All right. Can you hear me?
Yeah.
Perfect. So I think I'm just going to start with a couple of things to answer some questions that I got through email. So this is let me just, yeah, there was a automatic transcript thing. I just disabled it. So a couple of things. Some of you asked me for the code like that we wrote yesterday. I will share that code. I mean, I have to let you know a couple of things. So the first one is let me share my screen so I can show you. So the videos of the sessions are being shared, are being uploaded, edited, and I trying to hopefully like make them available the next day of this session. So in case you are wondering if I'm going to share this videos, yes. I put everything on my YouTube channel. That is, it's called Diego Pinochet MIT. And there are like some playlists. So in this case, for example, I'm putting here the sessions like part 1 and part 2 of the things that we did yesterday. There is a part 3 of the things that we did yesterday. And that part 3 is the notebook that I will share that teaches you how to do what we did yesterday with the flowers, basically like training with like data set that you can classify flowers using convolutional neural networks. But in this case, it's using your own data. So I put some examples here. I mean, I will change a couple of things and I will upload that in the third video that it will
so
be.
You know, we only see a Zoom screen.
Oh, well, let me.
You're sharing something with us.
Thank you for that. Let me put this again, desktop. Ah, it was desktop 1, sorry. Now you can see this. So I will share this notebook that basically is like one that is cleaner, and it teaches you. This is the part 3 that I will. I will finish editing after this session. That it complements what we did yesterday. It's basically like an addition to what we did yesterday, and I will teach you how to use your own data and use convolutional neural network to create your own image classifier. It's quite short. Basically, it builds upon the mostly the same. So in this case, I'm just doing like a toy example, like classifying cards, playing cards. So you can get like, for example, here, I'm detecting that something is like, it belongs to a hearts type of card or clubs or things like that, or diamonds with a certain percent of confidence. Because today we're going to move to something different, but I just want you to know that the videos are being edited. Like the 2 parts of yesterday's session are, as I was saying here in my YouTube channel, Diego Pinochet MIT. You will find other resources that I told you yesterday that could be interesting for you. I have here, for example, last year's Digital Futures is a full list of 4 videos with videos that go from 1 hour to 3 hours or 3.5 hours around the topic of reinforcement learning, for example. It was mostly reinforcement learning. I did like a couple of presentations here, and then it goes like deep into code. I explain like what reinforcement learning is, but it's a good resource. So in case you're interested to learn how to, for example, use, in this case, I'm teaching reinforcement learning on Unity using the ML agents package, and we're doing from scratch programming agents. There are examples to control a robotic arm, for example, or to create like simple agents that show like emergent behavior to a drone example. So for example, how can you make a drone fly, learn how to fly to go to like a certain like goal using deep learning. So just like I did last year, 1 year ago, I put all my videos here in the channel, and I put the first two parts of what we did today, being the part one, the presentation, and the part two, the code. Today will be more mixed. I will start, and I will put in the part three the link. Today's session will also have a bonus that basically we will use. Today we will see generative adversarial networks. So I will start with a presentation about what generative adversarial networks are, how do they work, how do they rely, for example, on convolutional neural networks to work. And we will use the famous and super trendy StyleGAN to learn how to use it, how to code, but also I will teach you how to train StyleGAN. So that is that will be something like very useful for you. And then I will put a bonus, but I will teach you how to do something that is like a little bit outdated. That is a DC GAN. That is a longer coding part, but it basically it's like an addition to understand some of like some other concepts about this. And also I will teach you a specific exercise around how to use these results with, for example, a software package like Grasshopper. So as I was saying, we will have the third session on Monday, so I can see some results from what I teach you today. So I can give you like Friday, Saturday, and Sunday to experiment, train, and play with the data, so we can have a discussion, and I can teach you like more advanced techniques and some things that relate with machine learning and interaction, for example. So I will teach you, like a couple of things that I have in my notes. So we will go through that. But first, I would like to start with a presentation that is actually interesting. Can you see my PowerPoint?
Yes.
Okay, so let me swap this place. Okay, so I will start with this image, and what you're seeing here is the result of the research or the paper, Progressive Growing of GANs for Improved Quality, Stability, and Variation. And this is a paper from Nvidia research team on April 2018. So you see that roughly this has like 3 years. This is a 3-year-old thing. And this was a huge thing, not only for architects, but for many things around like the visual community or even like society. Why? Because in one of the examples, like the bonus videos that I will show today, these were the results or the better results that you could get with the use of generative adversarial networks when they came out, right? Like 2014, 15, I don't remember exactly like the year, but basically it showed like a lot of promising results. And I will explain the concept behind generative adversarial networks in a second. But basically they create like new images from data, right? And these were like state-of-the-art results, right? Images that kind of look like people, or some like really good images that you can see that they look like people, but other things that were like abominations, like this picture here, if you can see my mouse, or this like whatever, like images that look like from a horror movie. So what you see down here are examples of like the struggles, like basically like to train a generative adversarial network, basically are neural networks that don't classify anything. They don't do like predictions, but basically they generate new content. That was something like the next step in machine learning after we had like breakthrough, as I was explaining yesterday, of like having machines capable of detecting with a lot of confidence if something was like distinguishing like a cat from a dog. Or today we have like machine learning that can detect cars in movement, so you can use those for self-driving cars. There was a next step on how to generate new content, for example, and GANs help a lot. So one of the questions and what we're going to see today is like, how can we get actually like realistic images? What you see here, the people that you're seeing here are people that do not exist. These are completely fake images of people, right? They look kind of like celebrities. They look like pretty good in terms of the results, but if you start looking closely, you see that some things are kind of off. So for example, I don't know, like the eye, for example, of this lady, the unrealistic background, the ear of this guy like blending with the background. A couple of things, like probably this is like the most like realistic one. But all of this, just to give you like a little bit of content, chat, let me check the, is there a plan for Grasshopper about machine learning? Yes, there are a couple. I mean, I'm answering the questions in the chat. There are a couple. The problem with Grasshopper, and I will explain, for example, Lunchbox, they use machine learning, but a different type of machine learning based on data. And actually, yeah, like Lunchbox, what they use is something that is called, basically it's a library. It's a C# library that they implemented those methods to do like clustering, like k-means or nearest neighbors, some simple regression, like more like old school type of machine learning that is very useful for data purposes, let's say. It's a good plugin. There are others. I think like Dodo was one, but in general, they're kind of like limited because of most of the machine learning models that, for example, the ones that I'm showing you here are based on Python, and those are incompatible with Iron Python. That is the Python flavor, let's say, that is embedded in Rhino. There are ways to use Python 3, for example, or Python 2, like the regular Python inside Grasshopper, for example, using Grasshopper Remote, but it's extremely slow and it's like super frustrating. So I will teach you in the bonus video for today how to implement a good workflow to actually communicate from Python to Grasshopper. I will teach you how to code that, so you don't have to go through those like software packages that are super cool, but probably you cannot use with this. Anyway, so the idea of generating content emerged from the first implementation of generative adversarial networks. And the idea basically is that you will have something that is called a generator. So basically you will have two neural networks fighting against each other, or basically competing against each other. And you will have, on one hand, one neural network that is called the generator, that is in charge of, as the name says, it's like generating images or generating data, right? And that data will be generated usually from random points. So in this case, it will use convolutions to create data from random information, and that will be tested basically. Oh, and the idea is like the generator will produce images from sample points, and we want to train that generator. Basically, we want to have a generator that can generate something like meaningful, let's say, right? So in this case, you start with like random data, and then you can get, for example, to a handwritten digit like this one after the train. And the idea of how will you train this generator to actually create new content will happen through like the help, or basically by interacting with other type of network that is called the discriminator, that will be, or it will act as a critic, right? And that critic, basically it will judge, or it will give a score to the generated image to see if this image is like real or fake. Basically, that's the idea. One network produces new content, and the other one will basically rate that image to see, oh, this image looks like real or looks fake, right? So according to that, for example, if the image is not good enough and the discriminator says like, oh, I'm seeing like real data, and what you produce, it looks like not real data, it looks fake, so I will give you like a low score. So then according to that, the weight of our network, remember that concept that we saw yesterday, it will be modified through backpropagation and adjust to try again and again. So basically every time according to the calculation of the loss, of the optimization of the loss, minimizing the loss of your training, supposedly the generator will improve its performance each time. So basically what we're doing here, this is like the basic way, or how like generative adversarial networks work. You will have a latent sample. Usually, again, you start with random data. You can start from like more meaningful data. There are like several techniques to actually improve the training or get like better results. But usually you start with random data points. So the generator would produce like a random image, and that will go through the discriminator, but the discriminator also will get all the training data. So let's say you want to produce an 8, right, or something that is like 100 digit, the discriminator will take both images and it will say like, oh, this image is not good enough, it's fake. And then it will go back to the generator, and the generator will, well, the network will adjust the weights, and you will calculate again to get better and better results. So the basic idea of this network, of this interaction, is both the generator and the discriminator should compete, right? And Ian Goodfellow, actually, it was 2014, in the original paper, the inventor or the creator of generative adversarial networks came up with this idea. I think it was in a bar. That guy, after like having drinks, he went home and he coded this, and it just worked. And the idea is that these two networks will compete. One will try to, the generator will try to fool the discriminator, and the discriminator basically also will learn and will be like, will learn from the samples that the generator is feeding in order to also get better, so it doesn't get fooled, let's say, right? So here it says like the generator will try to fool the discriminator by generating real looking images, and the discriminator will try to distinguish between real and fake images. But it will do that while basically it's increasing its performance as well as a discriminator, right? So you see here, random noise, generator network, fake images, and real images from the training set. The discriminator will compare both. It will say like, not good enough or good enough. And you will get, in the end, hopefully, a good result. So you train GANs by minimizing the cost, and you alternate between training the discriminator and training the generator to trying to minimize the cost for each, right? The discriminator cost on each round is how far from 0 it rates the fake inputs, right? Plus how far from 1 it rates the real inputs. So those are two things that you're measuring when you're training GANs, and in this case, the discriminator. And the generator cost on each round is how far from 1 the discriminator rates the fake inputs. So in other words, as it says here, the better the discriminator rates the fake inputs as far from 1 as fake, the worse the generator is doing at fooling the discriminator. Considering that real a real image is 1 and the fake image is 0. So you will have, like, for example, steps in each cycle of the training loop, and you will perform a loop while you will first train the discriminator a little on a mixture of fake and real data, trying to score fakes as 0 and reals as 1. And you will train the generator a little, generating fake data and feeding that from the discriminator, trying to make fakes that the discriminator scores as real. And for example, like 2017, it was like the year of the generative adversarial networks, because knowing that you could produce actually, and this principle worked in the based on the Ian Goodfellow's paper, everything was working. I show you in the first and the second slide of this presentation that the results were, for example, I mean, a couple of things happened. GANs were really hard to train, kind of unstable. So this is why there was like a lot of websites with GAN hacks, basically like hyperparameters and like a lot of tricks to basically make the training more stable, because sometimes you were just getting, in the end, only noise, and you were getting something that was called mode collapse, where basically like the generator was getting good enough scores by generating only one type of image. I will show you a little bit of that. But basically what happened is that one of the main issues, like, you were generating only like low resolution images, like MNIST handwritten digits, right? And if you wanted to generate faces, for example, using that from that example that I showed you with those weird faces using deep convolutional generative adversarial networks, yeah, like it was taking like a lot of time, a huge amount of data, like a lot of images, and usually the results were like subpar. So in 2017, a couple of things started to happen. So for example, we had better training and generation of images, like with all of this like experience about training and making more stable and even faster training processes, we could get better images. And we started to see like different flavors of GAN, like LS GANs or BGAN, using some techniques to, for example, like generate still low resolution images but with more stable results and better results. We had also like some breakthroughs on, for example, style transfer, what I showed you yesterday, where basically what the generator is doing basically is learning the distribution or the structure of the image. So when you have that, you can create things as like StyleGAN, where you can basically move from or transform an image of horses into zebras, or zebras into horses, or for example, like apples into oranges and vice versa, right? Or have for example, a winter picture or a summer picture, and then convert it to like a winter picture, right? So we started to see like a lot of advances in that, and especially 2017, everything just like popped, and basically like there was a lot of research on that. We had also like other GANs, like image synthesis, for example, basically like sequence to sequence type of, like the famous text to image implementation. For example, here from a description, the small bird has a pink breast and crown and black primaries and secondaries. And we were getting like something that resembles still low resolution image of that description. And of course, the famous that is like super, I don't know, yeah, it caused like a huge hype, especially for architects, the use of pix to pix. Especially like for urban research, where basically you can have like a map, color that map, and get something that resembles a city. Very interesting. Or sketch something and get something that resembles a purse, and so on and so forth. But I wanted to show you here, basically, it's like how GANs work. So I want you to go to this website. I will actually go to that and I will post the link. So we can basically use GAN's. Let me get the website. I mean, you can write it, but I will just share it with you in the chat, because it's actually is quite interesting to see how it works. So I have another one that is like more graphically explanatory on how things work. So this is a website that it's a playground. It's pretty similar to what I wanted to show you yesterday with the convolutional neural networks. I didn't find the address. Probably they took the website down. But what you see here is, first you have a place to configure your data, the data that you want to use to actually train a generative adversarial network for new content generation. We have here, for example, you can select a data set. You have MNIST, Fashion MNIST, or CFAR10 that are like the most popular data sets to test your neural networks. Here, you have flavors of generators. You can have like something that works based on fully connected layers. So basically like all the units on one layer are connected to the next one, or convolutional. And also for the discriminator and for the generator is like kind of the same. And you have here some hyperparameters. In this case, these are like very good hyperparameters. Basically, the parameters saying that like the learning rate, right? Here you have something that is called the learning rate of the discriminator, and this is like a parameter that is highly sensitive, especially for GANs, that tells you how to or how fast, for example, a generator will learn something, or the discriminator will learn over time to discriminate between real and fake. And I mean, we can find like a lot of like literature, but also like blog posts or forums that talk about this, especially the GAN hacks, because you need to be like really careful with this. So after like a week of training, you don't get like super bad results in terms of noise or what I mentioned before, this mode collapse thing, where the discriminator basically only is capable of generating one type of output. You have like different optimizers here, for example, stochastic gradient descent, momentum, ADA, grad, ADAM, like different flavors. Here in this case, ADAM is the one that is used, and there is a normalization of the data. Remember that in this case, we're working with images, in this case, like MNIST, for example, are images that are 28 by 28 pixels and one channel, basically because these are grayscale images. And the normalization is between -1 and 1. Those are the values that we're getting. So you can see here that the MNIST data set has 65,000 data points or images, basically. The input shape is it's 28 by 28 by 1. We have 10 labels, and we have a pixel range between -1 and 1, being -1 black and 1 is white. And here you can test if you want to train using CPU or a GPU. The important thing here is that here we have the graphical explanation of what I showed you yesterday in terms of the models that we are using and how will you build a model. So this is a stack model, like a sequential model. And in this case, let's look first the discriminator. And here this is pretty useful. Let me see if I can, I hope you can see, but here, for example, it says like the input image. This is the input of your network. And it's saying that it takes a 28 by 28 by 1 image, right? And that input basically is also the output, right? Basically that is the input image, like, and the second layer, that is a convolution, right? Remember the convolution, it makes like from one image, it applies like first like random filters, and it creates a stack of convolutions, basically like of images, like filter images. And in this case, it takes that image, the 28 by 28, and what it gives you, basically, these are the parameters of that convolution. We saw that yesterday. It gives us an output, a 28 by 28 by 8. So basically, it's an image that has like 8 channels of information, right? So it transformed that. And then it goes through like a ReLU. Remember that this type of optimization gets rid of negative values. And then it goes through max pooling. So basically, this is downsampling layer, where basically you reduce the resolution. So you can see that here we are decreasing the information from 28 by 28 by 8 to 14, 14 to 8, going through that through that max pooling. And then you have another convolution. Again, you have like apply different filters, and then you're getting from a 14 by 14 by 8, you get a 14 by 14 by 16, or ReLU, max pooling, and you get half of the size of the data. And then you flatten this, and you end up with a flattened layer with 784 data units. And then you apply a fully connected layer that reduces basically those 784 points of data or units into a 2, basically in 2 outputs, right? And those outputs are either 0 or 1, right? Through all the process that I explained before. Then you go through like a softmax cross entropy. That's okay. We're not going to get into that, what we use that. I will explain it later in the third part, because we will use that. But that will be a bonus session that I will upload for you. And then you get a label, right? So basically, what I'm showing you here is that you start with an image, you process that image, and then you just like apply the classification as something is like either a 1 or a 0. If we look at the generator, and this is important that I explain this, the generator is different, right? The generator in this case is starting from random data, and it's starting with a list or an array of 100 values, completely random. Why? Because it was like that. I mean, right now there are techniques when you can start from, if you, let's say you want to generate an image of a building, you can start with the image of a face, of a human face. That's fine. But usually, I mean, that's also like super random. Why would you start with a face if you want to generate a building? But in this case, you start with a random vector, right? Of 100 data points. You pass that through a fully connected layer to transform those 100 data points into 784, and then you will apply ReLU, and those images then you will reshape the 784 into a 28 by 28 by 1, right? So you have now here, you after going through these 2 layers, you already have the information that makes an image, and then you go through a convolution, and then you increase the number of channels of the third parameter, right? With more information, you go through ReLU, you eliminate negative values, and then you go through another convolution that in this case will transform this, because of the parameters, into a 28 by 28 by 1 image back. And then you go through like tanh is an activation function, and then you will generate an output image. And that output image will be fed into the discriminator, and the discriminator will compare that to a real image, and it will give you a classification if something is real or not. So what are we watching here? We're watching here real images. So basically, this is the discriminator working. And the discriminator is right now comparing that real image with the generated images of the network right now. So basically what we have here in this simulation is an untrained network, right? It's just generating like a whatever, just like something grayish, right? So what I want you to do is actually to train this and leave this like open and train it to see, for example, how, oh, this is annoying. Let me put the do not disturb. So we will train this. So we know, so for example, now the discriminator is not very sure about like if what we're seeing is a 0, is a 4, so it's like not performing well, right? Because we're not getting actually like a real image. So we will train this. And how will we train this? Just pressing train. And you will see that after we press train, our browser, our platform will start showing us the stats of the training process. So we will see over time, and this is why I want you to press on train, and you will see that at some point this will start changing. And hopefully after, like at the end of this class, we will actually have this generating something that resembles handwritten images. The interesting part, you see how this is changing already? It's not that gray anymore. It's to see like the evolution of the training, right? Here you see like how the cost at some point increased a lot, but now it's decreasing again, the discriminator. So at some point it got like really bad at recognizing or discriminating something from fake to real, but now it's like getting better. And also like the generator is getting like better and better results. It started like really bad, around like 50 samples, right? But now it's like increasing, right? So we will leave this here. You will see later how this changes in a good way. But I wanted to show you something else. I will also share the link with you of this nice post that basically it lets you play with GANs as well. And in this case, this is exactly what I was showing you, how everything works. So in this case, you will see that you start with noise. Let me see if I can, yeah, I can make this bigger. It's like a graphical explanation. And I appreciate this. And I appreciate like the opportunity to show you this in a more graphical way, even though that this is not my work, but I know there are resources out there that explains everything, not using math, using like something that is more like easier to grasp with images. Is how this works. So basically you start with noise to generate something, and basically those samples are compared with real images, and the discriminator will recalculate the gradients, right, by discriminating if something is real or fake. And this will basically be recalculated. The gradients of the discriminator will be recalculated by the discriminator loss, and the generator loss also will recalculate the gradients to make something better. And what we see here, basically, here it says that each dot is a 2D data sample, and the background colors of grid cells represent the discriminator classifications, and green are likely to be real, and those in purple are likely fake. So basically, here's like you see how indicating with a vector how the information is basically like being transformed or moved in order to generate something. So we can also train this. We can actually, let me pick another example. We will see if we can, for example, generate a circle. So if I press play, we will see the evolution as well of this, starting from random data and feeding, right? The purple regions are the fake. Right now, the generator is generating that is like a line, and you see like how these points are moving, right? And they start basically like being overlapped with the real points. So you see that now it's kind of finding like a distribution, and you see also like the evolution of both, right? So what we want, or we are expecting here, is that the purple points will match the green points at some point, right? So I hope like this graphical explanation is like more or less clear. So I want to continue presenting this so we can move to actual code. The code is not so complicated, but it's like quite useful. So right now we started with this. In our simulation, if you keep it running, you will see something like this. Like over time, now we're like here, like close to like 3,000 examples. With 10,000 examples or steps, basically, you will get something that is like a more kind of like meaningful type of shape. And then with 100,000, you will get something that actually looks like an 8 or a 3 or a 9. And then with 200,000, you will get something that is actually better. This looks like a 3, for example. And you will see this evolving in your browser, so that is good. And yeah, I just showed you this. So at some point, look at this, for example, after like a lot of examples, this is actually performing in a decent way. But again, always the problem was this, right? This is the result of a DC GAN that I will show you how to do in the example. This is like a relatively small model, but it requires a lot of data and a lot of training time to create like this type of images. This is something that I got after, I don't know, training this for like a 14 hours or something like that. That are not very good results, but they resemble people. You can distinguish like features and things like that. So I started like getting like super really bad images, then it started like to get better and better over time. But even though that at some point you can see like good results, like this lady here, for example, or like this guy here, you see like abominations. This looks like, I don't know, like a monster. This is like a, I don't know, whatever, like black eyes. Yeah, some things that are like really bad. But this was useful also because what we're doing also is like learning a couple of things related to like the distribution of or the generation of a latent space, right? This idea of the latent space is basically like while you're generating images, you can start performing some arithmetic operations on images because you already know the distribution of the things that you created, right? You train a network to do that. You can generate an image of, for example, if you're training on people faces, you can generate an image of a man and then generate an image of a woman and basically perform vector operations, arithmetic operations on those two data points and create, for example, something that is like interpolation. So you can, for example, go from a man to a woman or a woman to a man or a king to a queen and vice versa, just by solving those vector arithmetics, right? Go from like a walking to a walk or swimming to a swam, right? There are papers that here you can check. But this is like very interesting because we started to see a lot of implementations and basically like more like evolution of the things that you can do with GAN, right? For example, this idea of interpolation, like going from something that looks like one person to the other, just to change, for example, like the perspective. Like if you're looking to the left, then you change, then now it's looking to the right, right? This was 2016, still with like very poor quality data, but it was possible. Or you can do things like this, like you have samples from the model of a smiling woman, then a neutral woman and a neutral man, and then you can get a smiling man as a result, just by performing those arithmetic operations, right? It's like this minus this plus this, you get this. Pretty awesome, right? And this was the base for a couple of interesting things as well. So for example, you can get pictures of a man with glasses and a picture of a man without glasses and a picture of a woman with no glasses, and to get, after a couple of operations, a woman with glasses. Again, super interesting. Or do style transfer, for example, or cycle GAN to move from horses to zebras. You see how this is a transformation, or going from apples to oranges, or going from like a picture to a Cézanne painting, and so on and so forth. Or this is like one of the most famous pictures, like basically how will you create like an image of, for example, here, like Vladimir Putin on top of a horse. And then when you apply the transformation, this was one of the problems with this type of things. When you do the transition, it basically creates everything as a zebra. Basically, it cannot discriminate. It cannot do like, it doesn't have like semantic understanding. There are now advances on that, on how to only apply, for example, this to the horse, right? Are there any questions on this? I will show you a couple of more things. If you have any questions, please tell me. I hope this is kind of clear. We see now in the simulation how things are working. So we will leave that producing stuff. This is still like kind of going slow. Are there any questions? Okay, if not, this is another presentation that I have that if you have, feel free to post it in the chat. It's okay.
I just have a quick question.
Okay.
Like when you're building the model, like adding layers and stuff, how do you you have different parameters and numbers, and how do you determine that?
Okay, that is a very good question. As I explained, like when GANs starting they became popular after the Ian Goodfellow paper, it was very hard to understand what was going on, mostly because of one reason. To generate an image, you started most of the time with random data, right? Random points. So at the beginning, it was like a lot of like fine tuning. And this is why, like in 2017, for example, with the emergence of like a lot of the boom of different GAN flavors, websites, especially GAN hacks, became highly popular because to train a GAN was super difficult. Usually, like it was super frustrating to invest like a week of training, and I'm kidding, like week, even like people training for almost a month, and then just getting like noise or things that didn't make any sense, or images that were not high quality, like the faces that I showed before. And basically, like new flavors of GANs, basically we're tackling that problem of the how unstable GANs were at the beginning because of the parameters, like learning rates, for example, it was one of the most popular, and they started to play with like different techniques. So for example, train, for example, the discriminator, like every other epoch. So it doesn't, or the discriminator basically with the learning rate that was lower than the generator, or vice versa. So basically you like swapping parameters in let's say during training time in order to get better results. But I will say that the answer is that it was a lot of trial and error, and then realizing and understanding better how GANs work. So after 7 years, now there is a very good understanding on how GANs work. And this is why, for example, in this presentation, we got to, I mean, right now, what I will show you is that we got to a point where things are pretty advanced. I mean, and if you're kind of familiarized with this, most of the efforts basically were focused toward this, like generating better and especially faster visual content. So I don't know if that answers, but basically it was like a trial and error at the beginning. So here, for example, right? This is the DC-GAN, Deep Convolutional Generative Adversarial Network, where you have the ground truth, right? Images, faces of humans, in this case, celebrities. You can recognize some celebrities here. If you're a fan of Friends, for example, this is the actor that played Phoebe's dad, or this guy is a famous actor, Peter Jackson. You can recognize like famous people here. And from that, you generate fake images, like people that do not exist, right? And in this case, you have like good samples and some not good, right? And this is a training that took me 12 hours to do, based like by replicating this paper that you see here. And again, like the parameters, I just use parameters from that GAN hacks website, because some people say that these are the ones that you should use, and you see that the results are okay, not very good, not very good, not very bad. But also we saw like that some new models were developed. For example, BGAN, 2017, the year of GANs, that were focused on like modifying architectures using different flavors of or different layers for app sampling stuff to basically generate not only 64 by 64 or 28 by 28 images, but something that is like a little bit higher resolution. And you can see here that the results were getting something better. They're still not perfect, but better, just by modifying different things and different architectures for the generator and the discriminator. BGAN is for boundary equilibrium generative adversarial networks, but they introduced like some novel techniques. Then, for example, we had another example. This was BigGAN in 2018. That was focused again on creating large-scale GAN training for high-fidelity natural image synthesis. And you see that we move now to something that was focused entirely on producing like high-resolution images, right? Not only like real images, but something that looks like kind of real, like a butterfly or this like kind of hamburger or the dog that is actually pretty good, or a landscape. Again, by applying like different architectures that I'm not quite familiar because I never studied this, but I know that at least like what was the intention, right? To build on top of GANs to create something with more resolution. And the images were like kind of okay. You see that they are kind of weird, like you don't know if this dog or wolf has 3 legs or how many legs, something that looks like in a spaghetti, like some good enough results, right? Something that it's a soap bubble, but you see that something is off because the soap bubble is kind of, I don't know, like perfectly round, but good enough. But that enable, for example, things like this, like as I was saying, because we are learning now the distribution of images, is that we can perform these operations to map one image distribution to the other. So, for example, to convert, in this case, a horse into a zebra, right? And this boosted again like a lot of interesting applications. But again, like the training, for example, was an issue, right? Taking like a lot of computational power. Patrick asking, do all GAN processes start with a generation of random noise? Usually, yes. Usually, yes, but you can start with other parameters. Like, I mean, you can start with an image to actually train the neural network to avoid starting from random noise. And there are some implementation, especially, for example, with StyleGAN, when using a real image, for example, from a face or a landscape, something that is like closely related to what you want to get, it helps a lot with the training. So in this case, again, like one of the issues, like now that we had like good resolution and we could perform stuff, interesting stuff with GANs, the challenge was like how to train better, because this was taking like a lot of time. And this is why this paper from Nvidia, people from Nvidia, was so important, because they introduced this idea of StyleGAN, a style-based generator architecture for generative adversarial networks. But basically here, if you read the abstract, so basically they were adding, or they were borrowing from style transfer literature, some modifications to the architecture to actually, sorry, let me do this. I have it in my note, like actually what was like, they borrowed, yeah, from, so basically you could generate like new features, like to get like high level attributes. So for example, when you mean style, so for example, if you're training a generative adversarial network to create a person, you can train this to learn high level attributes, such like a person's pose, for example, or like the shape of a car, or for example, like the structure of the human face, and also like a stochastic variation, in this case, of the generated images. So for example, to generate freckles or hair or some, I don't know, like wrinkles or things like that. And it enabled like other things like scale specific control of synthesis, right? Basically improve, it did show like highly effective in improving quality metrics, like the quality of the images, and basically like the way to control better that those arithmetic operations to create, for example, like a interpolation. So what I'm showing you here is a video of Corridor Crew. This is a super popular channel of these guys that they work with VFX, and they started to use this, and probably you have seen this, like the advancement of StyleGAN to get like highly detailed images, allow this idea of the emergence of deep fake, right? Basically, you can map a person's face onto another and generate something that looks real. I mean, if you pause the video, it doesn't look real, but basically this is a guy that is not Tom Cruise, and they just train a neural network to generate like someone that looks like Tom Cruise. And this was like an early implementation of this. And they discuss about how they did it. They hired a stunt double of Tom Cruise, and then they just use a lot of images from Tom Cruise to generate something that, yeah, over there, it looks like okay, right? The eyes look kind of funny, but it was like a very good thing. And because you can learn those features, basically you're not learning only like the global distribution of an image, but you're also like learning. I mean, when I said like you, it's like the GAN, the model. Now you're learning like specific details, right? Beyond the general, like a pose, for example, but also like the shape of an eye, or if you have glasses or things like that, is that you can create amazing things like this. Control Shift Face is also a YouTube channel that use super creatively this idea of like deep fakes, where basically they are mapping the face of Freddie Mercury on top of Rami Malek, the Mr. Robot actor, right? And you get results that are like just amazing. Just look at, and this was done also with StyleGAN, and they have a really good channel. And you see here's how they took like a lot of information from Freddie Mercury and also Rami Malek, and they were able to actually do that translation. And you can see like how basically they use this to create this transition that is actually like, I don't know, it's weird, but at the end it's amazing. And of course that there are like a lot of like moral and ethical like and issues about like the use of deep fakes, because we have seen this widely used now in the porn industry, where basically they started to map actresses' faces on top of like porn movies, and that was of course like super bad. So now, for example, Nvidia has like disclaimers that you should use this in a responsible way. But those advances, and these are the last slides before we start actually doing stuff, were basically making this I'm sorry, we were having good results, but still we had like some weird let's say things that I will talk in a second. But again, by learning not only the distribution of an image, but also like a specific high level or low level features, like, I don't know, like the shape of the eyes or things like that, is that we could, for example, like make transformations. So makes, for example, people to create like this one, or for example, transition from this guy to this guy, or even like change the color of a person, right? To play with that type of things. This is why I show you on the other slides how come, for example, you can remove the glasses of a person. And we came to like state-of-the-art implementation, and this is something that I will show you how to implement today. This is a real image. Sorry, this is a fake image. But if you see this, you cannot. I mean, if you present this to anybody, of course, if you present it in the context of like teaching machine learning, you will say like, this is a fake image, of course. But if you show this to your mom or someone that never heard of this, they will never deny that this is a real image, even though this was a fake produced image. And this was produced by StyleGAN 2 that introduced like new advances in training. And one of the advances was also that how can you train with less data, right? If, for example, for a DC GAN, you needed like 100,000 images, you can train something like good enough with, let's say, 1,000 images. That was a huge improvement because now you can get, basically you can decrease the number of data that you're using, but also increase the resolution. And you can see like some things like this. So basically what introduced is something that I actually taught you yesterday. And that was the purpose, like first to understand convolutional neural networks, but at the same time to understand other techniques that were introduced here. And this is one of the major breakthroughs of StyleGAN 2, is that they introduced the idea, if you can see it here, this AUG, it stands for augmentation. They introduced this idea of data augmentation inside the training process. So instead of having 1 million images to train your model, with 1,000 is enough, because you will perform data augmentation during the training process each time to basically fool the network to work with more data, right? So for example, you see here that how from a cat and just applying like contrast things, or just like shifting the picture or rotating and changing the colors or squishing or performing like weird operations to image, you will augment the data. From one image, you will get more, right? So you don't need like a lot of data to train your GANs. Of course, like more data will probably make you get like better results, but I mean, instead of training for months, I think that Nvidia model that creates that girl's face resolution, or maybe it's a girl. I think, yeah, someone told me once that it took like 2 months to train with Nvidia GPUs. So imagine, it's like crazy. Right now we can train models in 24 hours to get good enough results. So even though that we get like very good results, you can, if you see this, you can see that, oh, these are like very cool images, very high resolution, very good, very useful, for example. But you can, if you look closely, you can start seeing some like very weird stuff. So for example, like dreamlike, blurry backgrounds in the case of the picture A, right? Basically, you can start like seeing this type of things, like the difference in the earrings, right? Or, for example, like, what is this, right? It's like a weird reflection. It's like an evil deformed twin on the shoulder of this guy. Or, for example, here, like the eyes of this person, like the eyelashes. Those are things that makes you basically realize that things are kind of off. So today, I mean, StyleGAN like made a lot of improvements to actually solve those things. So we will learn how to code and train with our high-res images using StyleGAN 2, implemented in PyTorch. We will see this, another framework or platform. And I will show you 2 things. First, I will show you Colab. The Colab is what we used yesterday, but also I will teach you how to use Runway. And I will teach you also a couple of things and for that we will need to use Visual Studio Code, but I will give you the directions so you can install that after we take a break. We will take a break in more or less like 15 minutes. I will show you first Runway ML. Have you heard of Runway ML? I can see your faces. I don't know if you're there, but will be nice. Have you heard of this?
Yes.
No, I've never heard of it.
Yeah.
Okay, Runway ML is a company that was created a couple of years ago by 3 people. Basically started as a thesis of Cristobal Valenzuela at the ITP, Interactive Telecommunications Program at NYU. Cristobal was a former student of mine in Chile. He's a former student of mine, a very, very nice person, a colleague. Then he became a TA. He was TAing for me. Then he became a colleague, a friend, and I'm really proud of the work that he produced here now with Alejandro Matamala and Anastasis Hermenidis. They created this company based on Cristobal's thesis that basically let you use machine learning or deep learning models without knowing anything about coding. So they are more focused now. I mean, their motto was like use machine learning for artists. Now they are more into like general creative purposes. Like for example, like the movie industry, they have a dream of like making this tool the next special effects type of tool for movies. They have worked with New Balance, Google, IBM, and many companies. And it's a very nice platform that now they move to almost like a completely online platform. If you are interested in testing this, you can create your account. You will have some credits. Maybe you can talk to Cristobal so I can get you free credits. But you see here is that when you enter Runway, sorry, and now they change the interface again. That is now good. Oh yeah, they have something that is called SQL. Apparently, they created now a tool to create like movies, and this is the ML lab. So you have like a lot of models here. And the way this works is that, I don't know, let me just do or show you one sample of this. You can do, for example, style transfer to create like an anime type of images from your picture. So you just add this to like a workspace. It's like with simple clicks. So I can say like, oh, I want this to use my camera. This is using my second camera, and then you run the model, and everything is being processed on the cloud, right? So this is using a model strain on StyleGAN to actually do the style transfer. So at some point, this should start showing here, for example, my face as an anime character, hopefully, or maybe it will show something like kind of weird. Sorry about the messy background that I have. These are my research projects. This is my office for the PhD. So yeah, this might take a while because it's sending the information to the cloud and it's getting back the process information. So that's the thing. I mean, you can do machine learning with a Mac, just like we're doing with just a Colab notebook. The good thing is that, I mean, it's relatively cheap. You can train a model for $10 and they will do it in a couple of hours, while it would take like a day in your computer. So if you take into consideration like the electricity that you will use, your time is super cheap to train stuff here. So if you're interested, like shoot me an email and I can probably get you like some credits to start exploring a little bit more. I will leave it like working so I can move into something else. But the good thing about this, and this is what I mentioned in this. So for example, if I see my models, I have a couple of things trained here. And for example, here, images of Frank Gehry buildings or Zaha Hadid. And these are the ones that I use for a previous workshop. So for example, I was able to train like something that interpolates through different Zaha Hadid-like generated images, right? And I just selected like a specific Zaha Hadid images to do this. And it was like actually quite interesting because I wanted to get like this sort of aesthetic. So basically what happens is that when you use this type of, or basically you use a StyleGAN, you can generate a landscape of images, of generated images, And then, for example, you can select a couple and ask the computer to do a random walk to transition from one image to the other. So I pick a couple of vectors here, and I just created using Runway this transition. That could be like highly evocative, for example, for creative purposes. That's what I'm trying to basically say. Let me show you one more thing so we can start coding. So when you train, for example, you can use models uploaded by other people or by them, but also you can train on image, on text, or object detection. So in this case, for example, I have my model trained on Frank Gehry's images, and you will see that here are images generated by this, but also, and this is very important for what we are going to use today, you can use or you can get checkpoints, right? What is a checkpoint? Basically, a checkpoint is a file that contains the information of the architecture, but also the weights of the model. So you can do something that is called transfer learning. So you will see a lot of implementations of transfer learning today, or you see a lot of implementations. So in this case, for example, like Runway is providing you the already trained models so you can use in your own model or in your own like software, right? So in this case, for example, because this is the file that contains the information of the trained network to produce Frank Gehry-like images, I can train it on Runway faster than I will do it on my own computer, and I can download it, right? And I will download this as a PKL file. I will save it because I will share it later with you, so we can create like Frank Gehry image-like images with my model. But then I will show you how to train your own. So be prepared for that. So now, what I want you to do, because this is still using my model, and it's not doing anything, probably because the image is too big and the internet is like kind of slow. Let me lower the resolution. Yeah, probably it's not working right now. Probably it's because my connection is kind of slow. Anyway, I can show you how to use it later. But what I want you to do is to go to a Colab. So I will go to Colab. Colab.research.google.com. Yeah, Natalia, there is a preview, and I put it, but it was not showing. So anyway, it doesn't matter. I mean, I can. There is a Runway tutorial also on my YouTube channel in case you want to use it. So I will start a new notebook, and for this one, we want to configure this to actually use the GPU. So if you open your Colab first, we're gonna rename this. We're gonna call it like Futures session 02 GANs. So we will go to edit, and we will go to notebook settings. And here you see that I'm not using any GPU. So basically we want to use a GPU to configure this. And for now, we don't want to use high RAM. We're going to leave it in standard because we are probably, yeah, it's not necessary for now. So we will just like configure here the GPU, and we will save this. And we need to connect because we need to basically ask for space or machine allocation. So I will show you a couple of interesting things related to that. So it's initializing. Let me close a couple of things that I have here. What we want to do before I will show you how to train, but we want to do a couple of things. The first thing that is interesting, because that will show you, this is like the pre-step, is checking the GPU, right? So this means that I want to know what type of GPU I am using, or if I am using a GPU. So the good thing about Colab is that you can use kind of like terminal commands as they were like Python commands, meaning that, for example, you can do the exclamation sign, you can write Nvidia SMI, and this is a terminal line of code. If you're familiar with, for example, Ubuntu or like Linux in general, like Arch Linux or other distributions, you can you know that Linux uses a lot the terminal, right? The terminal basically is this, right? The terminal is this, so you can write like ls to check ls to check, for example, like the content of a folder and so on and so forth. So usually this is a line that you will write on Linux to check what type of GPU you are using, or the GPU stats, let's say. So, and we'll put a comment here, it's like run this to check if you are using a B100. I think those are the GPUs that you have, like the P100 or T4. Those are the GPUs that usually Nvidia puts available for you. So if you run this, you will see that this is telling us a couple of things. This is using a driver version. This is using actually CUDA. And CUDA, I didn't explain that yesterday, but I mentioned it. CUDA is a toolkit for parallel computing, right? Developed by Nvidia. And it works with this idea of parallel processing using GPU power, a lot of GPU cores that have this platform, right, for the development of highly efficient parallel computing based on C++. You can do like amazing stuff, especially for image processing or big data, right? So there is a special toolkit, and usually like PyTorch or others, they require using CUDA. So one more thing. For example, if I go to PyTorch, that is an open source machine learning library based on the Torch library used for applications such as computer vision and natural language processing, primarily developed by Facebook AI Research. It's an amazing framework. I like it way better than TensorFlow. So, for example, PyTorch is super easy to install in your system. We will go through that not today, but in the third session, how to do this locally in your computer. But basically here you see that it has like a lot of like implementation. So for example, you can have like the stable version. What is your operating system? If you're using Linux, Mac, or Windows. If you're using Linux, you have access to more things. So you can download with the software package manager, such as Conda, PIP, LibTorch, or from source, download it from source. Let's say PIP, you can configure the language if you're using PyTorch and Python or C++ or Java. For example, if you're an Android developer, if you know Java, you can use PyTorch with Java. That is cool. And here, for example, this is important part. You have different versions like CUDA 10.2 that will work with other models. Right now we're using 11.2. That is good to know because some models are not compatible with this version of CUDA. ROCm, in case, for example, ROCm is something new that is part of AMD's, the competitor of Nvidia in the world of GPUs, that they now release like this, like the CUDA-like version of AMD for this. So just so you know that what we're using today. And here, for example, is telling us that it's using a Tesla P100. That apparently and again, sorry that I'm taking time explaining this, but this is actually quite important. So yeah, so for example, you see that the T4, for example, outperforms the P100. B100 is actually way more faster than the P100 GPU. So we're using the lowest GPU available for this. I mean, probably because they know that we are not using high RAM usage or stuff like that. Sometimes if you get lucky, you will get access to a B100. I never get access to a T4, but I think this is good enough for training or doing what we want to do. But sometimes, I mean, Google will, I think Colab will understand what you're trying to do and will try, if you're using Colab Pro, and will allocate like a better GPU for you. So this is good. We want to start with that. But also, because we are going to work with data, and usually when you start a session, so what you see here when you start a Colab, if you press here in the folder, you will see a directory, a folder that has like sample data. This is something that you can use to start. For example, you have the MNIST data set, the California housing test, some files that you can use if you're starting with machine learning. But this is temporary data. Like you can also upload files here, right? You can upload whatever you want, like images or whatever. The only problem with this is that after you close your session or Colab kicks you out, you will lose that information, right? So this is temporary information. So you have an option here to enable your or mount your Google Drive. It's like connecting your Google Drive to Colab, right? And you can do it by pressing this button, but usually, I mean, sometimes I find it useful to show you the process of doing this by code. Basically, it's exactly the same process of like using this, but sometimes you will find this implementation as well. So that's the, let's say like the step one, right? So step one of our process, we will be mount Drive in Colab. And to do that, I will create a cell for coding, and we will do the following thing. We need to say like from Google that Colab import drive, and then we'll say drive that mount, or in a new line, drive that mount. We want to specify like a path. So we will say like mount this in content drive. So if we write this, I'll put it big so you can see it better. If we do this, we will be mounting the Google Drive. So we can use our Google Drive to store files or to basically save anything we produce during the training. Otherwise, we will lose that information. So we can save checkpoints to use it with another software. We can use data set that we keep inside our drive, and so on and so forth. So in this case, if I press this is like go to this URL. It sends us a message. So we need to click over here. You need to pick an account, your Google account. It asked me to sign in. Okay, and it will give you a code, and it will be a different code. So I don't mind like showing you this because there's nothing private with this. I will just like copy this code and paste it here and press enter. So this is this is an authorization token, and this token will make will give the authorization to Colab to actually use my Google Drive, and this will take a little bit of time, right? So now it says that it's mounted, so I can refresh this, And I can see now that I have my drive, and my drive is a mess, but it will show me like all the things that I have in my Google Drive. So I can use that. So that is actually super cool, because everything that I produce, I will make sure I copy it to a folder over there. So for example, I can resume training, I can use it with other code. But also we want to check if this is working. So we will do something that is called try. We will ask the computer to try to do the following from that on Google that Colab are we using? No, we're not going to do this today because we're going to lose time, important time. What I want you to do is to do this step and to see if it works. Because now we are going to go. We're going to perform the next step. Actually, you will find the code quite simple for StyleGANs, especially for the training part, right? Let's say this is step 2, because Nvidia is like making our life easier. So step 2, it will be cloning StyleGAN. We will use a special flavor of StyleGAN ADA and something called Ninja. I will explain what Ninja is. So this is the step 2. What we're doing here, we are downloading a repository from Nvidia that contains all the necessary files to actually use StyleGAN. So I will do that by using, again, this terminal command. So I will say like git clone. If you're familiar with GitHub, you see that this is a command to clone a repository. So basically you upload your code to this. There are places like Bitbucket or GitLab, in this case, like GitHub, where you can store your code if you have something open source, for example. I'm sure you're familiar with this. If not, there are like many of resources to actually see what GitHub is about. But in this case, we will clone the repository like manually here by doing this. It's git clone HTTPS, and here the address is github.com/nvlabs StyleGAN ADA pytorch. You write it. You write this like this. I will copy this line in case it's like you get like some typos. And also we will do pip install Ninja. I will copy this line in the chat. So if I press play, you will see that this is cloning, the repository is cloning all the, oh, I had a typo. Let me see, StyleGAN. Oh, this is StyleGAN 2. Sorry, I had a typo. Just give me 1 second here. Why it's not copying? There you go. Now, if I press play again, yeah, now it's cloning the repository. So you see, this is connecting to GitHub. It's connecting to this repository, to all the files, and it's downloading everything to have, in this case, StyleGAN ADA pytorch. What is StyleGAN to ADA? This is, if we go to the website from Nvidia, basically this is what we are downloading now. We're downloading the pytorch version, and basically this has an adaptive discriminator augmentation. So remember this image. Actually, I took this image from here. What it's doing is that in real time is augmenting data while the training process is happening, right? With the discriminator. So it makes you train faster and also with less data. That's why the name. So when you clone this, and also what is Ninja Python? Ninja is an IDE for recursive, not just another IDE. It's a cross-platform integrated, designed to build Python applications. It provides tools to simplify Python software development and handles many kinds of situations thanks to its rich extensibility. So basically, we can do a couple of interesting things for generating information using this package that is called Ninja. That it comes from, again, Ninja IDE is not just another IDE. Weird name. So once we have this, we can check that we have the files. This is very important because sometimes you will find an error specifically related to this DNN live. Basically, this is CUDA implementation. So if you don't have this installed in your system, usually on Windows, it's a pain to install, not anymore. But the easiest way is to just do everything on Linux. If you're really interested in actually going or doing a deep dive on the world of machine learning and deep learning, you need to use Linux. You have docs, basically here, metrics. You have code for utils that we are going to use stuff for the training. So you see here, you have the file that does the augmentation, the one that deals with the data set, the one that deals with the loss calculation, the networks. So just to show you a couple of things before we take a break in 5 minutes, it shows you like all the imports. This is just like pure Python code. We can code this, but it will take like hours to code all of this. But you can see that here you have like the layers, like the fully connected layers, the convolution layers, and so on and so forth. And at some point you should have like also as a class the generator and the discriminator. Yeah. So for example, here you have the class that actually creates the discriminator, and it uses like other subclasses to create what we need to train. It will take like a while to actually code this. So we're not going to do that today. We want to use this and we want to do something with this. So with that, we are okay. So if you want to verify your files beyond just like looking the files here, we can do a couple of things. So for example, to verify the files, we can just write another things like ls content / StyleGAN ADA pytorch 2. So basically this will list all the files that we have in this directory. So if we see something like this, we know that we are golden. We are good to go and we are good to start using this. Are there any questions? Are you there?
Yeah, sorry, what does the ls mean?
ls, it's a command to basically list the files. I don't know like what ls specifically is, but that's something that you use in a terminal to list the file. So for example, here, if I use it in my computer, I said like ls, I'm in the root folder of my Mac. And yeah, it shows you like all the directories that I have here. So that's it. It's just like terminal syntax for watching your files in a directory. Okay, right now here we have, what time is it? It's 12:05 p.m. So we will have, let's do a 15-minute break, and we will continue with the second part of the code to actually use with a pre-train thing. And I will show you how to train with your own data. That is something that I want you to do. And I will also upload, hopefully tonight, these videos, but also a third part showing you the other things that are useful for you to work during the weekend, so we can have a discussion and also learn something like super interesting on Monday in our last session. So 15 minutes, and I'll see you then, okay?